In a world where robots are no longer machines but sentinels of safety, surveillance, and autonomy, engineers stand at the front lines, designing not just to build but to optimize. Lighter, smarter, faster. That's where design meets intelligence through simulation, computer-aided design, and motion analysis. Thanks to Altair's powerful tools like Inspire, HyperWorks, EDEM, Archisoft, and many more. Work with me as I took on the challenge of optimizing an all-terrain robot for maximum performance and real-world reliability. By the way, I'm Amao Ibrahim Oladipo from the Department of Mechanical Engineering, University of Abuja. For my entry submission in the third quarter Altair Student Contest, let me walk you through the process I followed to optimize an all-terrain robot. The robot is designed for all-terrain mobility. It consists of an electronic compartment, chassis, joints, and tires. I proceeded to motion ribbon 2 in Altair Inspire, where I defined the ground, rigid bodies, and motion-driven joints. I then configured the motor type to speed and assigned its function using a table. Contact between the tires and ground was established. Then I adjusted the parameters in the property editor. Finally, I ran the motion analysis to evaluate the robot's performance under dynamic conditions. This is the result of the simulation, which shows that the robot is moving across the ground terrain, demonstrating interaction between its tires and the surface. Each component of interest was analyzed using the motion results. The stress distribution on the frame revealed that von Mises stress concentrations were significantly higher around sharp corners, holes, and edges. What a perfect recipe for failure. This instantly reminded me of a machine design class where we covered variable stresses in machine parts in our course material. Now let's return to the analysis. Displacement results were reviewed along with the factor of safety, which had a minimum value of 13.3. This indicates that the frame can be optimized by reducing its weight without compromising structural integrity. Lastly, I needed to create callouts for the tire rim, which I copied, pasted, and edited in an Excel spreadsheet, then saved as a CSV file. The following are results, which include a color legend from the structural analysis of the frame and joints, along with a table summarizing von Mises stress, displacement, and factor of safety. I applied topology optimization to the frame and joints, ensuring that the mounting zones were preserved and setting appropriate manufacturing and shape control. For the tire rim, I used an implicit modeling approach driven by a CSV file created earlier, which I imported into a point cloud to guide the design. To address dust and water exposure around the electric motor housing, I also applied an implicit approach to the mentioned component. The optimized geometries were cleaned using PolyNURBS, and the following are the final results of the optimized components. All the optimized components were assembled and validated by running structural analysis again. These are the results comparison between the original and optimized components. With the optimization completed, I proceeded to validate the geometry for additive manufacturing using Altair Print3D environment. Support direction, overhangs, and build orientation were analyzed to reduce the printing time, avoiding unsupported regions, and optimizing the print setup. The final result can then be exported for manufacturing. With the optimized design, I achieved significant improvement, around 40% mass reduction, 40% less power consumption, and over 30% savings in printing cost for major components. That translated directly into improved system efficiency with lighter parts, lower energy draw, and better performance. It reminded me of something Dr. Deji Aremu said during the HEPSA FEA training. The more load your car carries, the more fuel it consumes. Well, in my case, by reducing the weight of my robot, I reduced its power consumption. This is the workflow I followed for the process. Along the way, I discovered a few helpful tips that made the work easier and more efficient. Altair Inspire made the entire process seamless. Honestly, this is a great tool for product design, especially for startup companies. From this project, I've learned that reducing weight doesn't just improve strength, it boosts efficiency, lowers power consumption, and cuts manufacturing costs. As future work, I plan to analyze the robot's interaction with different terrains such as sand, gravel, and soft soil using Altair EDEM. Special thanks to Altair, Dr. Deji, Professor Dagwa, and my family. Thank you.